Okay, so 5 or 10C is all about proof by equivalence. And a lot of this is very algebraic. If you want to kind of follow this right here, this is just kind of basic algebra. So one of the things that, so let's start up here. In proof by deduction, we are only concerned with moving in one direction. That means to say if we want to show two statements, A and B are equivalent though, we have to do both separately. We have to first do A implies B, then we have to do B implies A. However, this is a good however. If we can construct an argument so that each deductive step is an equivalence, we can do it at the same time. So for example, x plus 1 to the third power, if we were to distribute it all through, is x to the third plus 3x squared plus 3x plus 1. We're keeping the right side the same. Then what we can do is move the x to the third and the plus 1 over to the left side. So the x to the thirds drop, the 1's drop, and we're left with 3x squared plus 3x equals 0. Factor out the GCF, x equals 0 or x equals -1. So this chain of reasoning relies on the fact that the two equations are equivalent if they have precisely the same solutions, and two functions are equivalent for every x belonging to the reals. All right, so there are certain things that we can do for equivalence: add or subtract, multiply, divide, or substitute for an equivalent subterm. So and that we see here and there. What we can't do, we can't square both sides because we lose positive negative stuff. And we can't square root both sides. So be very careful about that. Example 2 says find the smallest positive integer for which this equation only has real solutions. Now let's think about, when does a quadratic have real solutions? We can have imaginary solutions, we can have one solution, we can have two real solutions. To me, that's talking more about the discriminant. The book chooses another way to do it, but I'm going to talk about if the discriminant equals 0, there's one real solution. If it is greater than 0, there are two real solutions. And if it's less than 0, there's two imaginary or no real solutions. So what I'm going to do, I'm going to say A equals 1, B equals A minus 2, and C equals A. I'm going to use my coefficients of my x. And I'm going to use my discriminant, B squared minus 4AC. And I'm going to set my discriminant greater than or equal to 0. Because it could be one solution or it could be two real solutions. Either way, it's going to be real. All right, so my B is A minus 2 squared minus 4 times A times C. Lots of ABCs here, sorry about that. I want this to be greater than or equal to 0. Now I got to simplify this whole thing. So when I square a quantity, I'm going to combine like terms. And we're looking for the smallest positive integer for A. So we need to solve this for A. Now, honestly, the easiest, this is not factorable to solve for A. So I'm going to complete the square. Leave a blank, move the -4. the other side, take half of my middle term, a minus 4 squared, add 16 to both sides, greater than or equal to 12. Now, be careful, when you square root both sides, this is an inequality. Typically, we have our plus and minus. We still need that. On the positive case, my inequality stays the same, but I don't put just the plus or minus and keep the greater than. The negative case, I switch the inequality. So my positive square root of 12 stays greater than, matches the equation. My negative case, I switch the inequality. All right. So here I would get a is greater than or equal to 4 plus the square root of 12. And that's approximately, just a second, 7.46. If I solve this one for a, I get 4 minus the square root of 12, and that's approximately 0.536. Now remember, we're looking for the smallest positive integer. So if a has to be greater than this, what integer is that going to be? When a equals 8. On this side, a has to be less than this value. That would be a equals 0, but it has to be a positive integer. So this one doesn't count, and my only solution is 8. So this whole problem was really sneaky, but I'm going to tell you, I see this kind of stuff throughout the IB test. So that is something that I would definitely take note of. And even if you just recognize this to be true, if you can get to this point, you're going to get your points. You might not get all of them, but you're going to get your half that you need. Okay, so this discussion is showing you two different types of proofs. And it shows the same thing. In a direct proof, we start with the hypothesis and work forward. So for example, if I want to show if A is less than B, then A has to be less than A plus B over 2. This is starting with the hypothesis, working our way down until we can get to the right answer. All right, so one of the things that a lot of people kind of just say, well, how do I know how to take these steps? You always look at the beginning and look where you're at the end. See how at the end we need it divided by 2? So that's why the first step is you divide by 2. Now, they have this little caveat here where 2 is greater than 0. That just means you don't need to switch the inequality. Then we would have B over 2. So notice we need an A added over here. So we just added A over 2 to both sides. But half A plus half A is just 1A, and we get our conclusion. You see proof by contradiction, which is also called an indirect proof, quite often. So a proof by contradiction, you assume the opposite of what you're trying to prove. So in our hypothesis, if A is greater than B, then this is true. We're going to assume that the conclusion is false. So what's the opposite of less than? If A is greater than or equal to A plus B over 2. And then we work our way backwards and we show that it contradicts our hypothesis. So this time we're going to get rid of the 2, so multiply both sides by 2, subtract A, and we end up with something that contradicts our hypothesis. So if the work contradicts the hypothesis, then the supposition has to be false and the alternative must be true. That's 10C. All right, 10D is all about definitions and using definitions appropriately. So in math, I've always been a stickler about defining our key terms. I mean, you think about all the notes you've taken in my class, holy smokes. So first of all, a rational number can always be written P over Q. An integer is even if n equals 2k for some integer k. All even numbers 2 can go into, so you can take 2 times some number to get that integer. And then it's odd, 2k plus 1. The even number plus 1 can always get us an odd number. So why is it so important that mathematicians use the same definitions? You think about, theory of knowledge for math is so critical. We have to have the same definitions or they will lead to different conclusions. Everything's based on your definition. All right, so I just got done showing the juniors how to do this using an infinite sum, but I'm going to show you another way with this one. This was the way we always used to do this in pre-algebra. All right, so let's assume that x equals 0.131313 and so forth. So you choose however many values are repeating, and we're going to multiply this whole statement by that power of 10. Since there's 2 digits repeating, I'm going to multiply by 10 squared. And what that does is moves this first 13 over into before the decimal. And it still keeps repeating. And then what we do is we subtract 100x minus 1x is 99x. We subtract 13 minus 0 is 13. Then these all line up. That's the reason we multiply by 100 is I wanted the 1s to line up, the 3s to line up forever and ever and ever. And I get 99x equals 13. So x equals 13 over 99. Because 13 hundredths repeating can be written as a fraction, then that belongs, hence, therefore, that belongs to the rational. You know why Q is for rational? What's the one Q word in math? Quotient. What does quotient mean? The answer when you divide. P over Q. All right, so speaking of rational numbers, prove that any sum or the sum of any two rationals is also rational. All right, so how do we define rational? Let's just say we have x and y are rational numbers. Sum of any two rational numbers. We're starting with, this is our hypothesis that x and y are rational. If x and y are rational, then x can be written as a ratio and y can be written as a ratio. And this is also where all my variables p, q, r, and s have to belong to the integers. And z is the German word for number, starts with z. That's why they use z for integer. Okay, so the sum of my two rationals, because that was my hypothesis, the sum has to equal a rational. Well, x is p over q, y is r over s. These are all integers. Now I can get a common denominator. So I'm going to multiply top and bottom by S, top and bottom by Q, and I get PS plus RQ over QS. And if these are integers and these are integers and these are integers, they're all integers. If these are integers, then P times S belongs to the integers. RQ belongs to the integers. QS belongs to the integers. So this ends up being a rational number. We'll just say capital P over capital Q. All right, so kind of confusing. Here's just some general things that you can kind of do similar to what I did in the earlier problems. Don't be stressed about them. We'll talk about these on Tuesday, and we'll go from there.